Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I really want you to just take a moment right now and picture the moon. And I don't mean a high-resolution photograph from some astronomy textbook, but the actual moon you see when you step outside on a clear night and just look up.
Right, just that familiar glowing sphere we all know.
Exactly. To the naked eye, it's just this glowing, cratered ball. It's undeniably beautiful, but it also looks like a completely dead, dusty rock, just sort of floating in the cold void.
Yeah, and I mean, humanity has grown up with that exact same image for tens of thousands of years. We look up and we basically just see a monochrome desert.
We do. But okay, what if you could put on a pair of magic glasses? What if the second you slip those glasses on, that pale gray rock completely transformed?
Oh, I love this analogy. It's like flipping a switch on the universe.
Right. Suddenly, you aren't looking at a lifeless desert anymore. You're looking at this vibrant, neon glowing map of hidden chemical elements spreading all across the lunar surface.
You'd see pockets of brilliant blues, sweeping streaks of radiant reds, deep pools of vivid greens.
Yeah, exactly. You would be seeing the actual chemical makeup of the moon, glowing in real time. It would completely rewrite our understanding of our closest celestial neighbor.
It's an absolutely stunning visual to imagine. It really is. And what is truly incredible about where we stand right now in astrophysics is that we are no longer confined to just imagining it.
We're building them.
Yes, we are actively building those magic glasses.
And that is the massive breakthrough we are getting into today, because a team of researchers at Tokyo Metropolitan University, specifically led by Ori Toida and Professor Yuichiro Izoe, have developed something that frankly feels like it belongs in a sci-fi novel.
It really does. It sounds like pure science fiction.
But it's real. They have created this highly compact X-ray telescope that is capable of giving humanity its very first complete, comprehensive chemical map of the lunar surface.
And we really need to establish the stakes here right away. This effort, it's not about capturing prettier, more colorful pictures of the moon to just hang in a gallery or put on a magazine cover.
Right. It's not just for the aesthetics.
Not at all. We are looking at a fundamental paradigm shift in space exploration. This specific technology is going to completely change how we understand the moon's deep, violent geological history.
Which is fascinating on its own, but there's a practical side too, right?
Oh, massively practical. Perhaps even more importantly for our lifetime. The data this telescope gathers is going to literally dictate the moon's potential to support human life in the very near future.
Okay, so let's unpack this a bit, because whenever someone says, X-ray telescope, my mind immediately goes to these massive multi-billion-dollar orbital observatories.
Oh, sure, like Chandra or XMM Newton.
Yeah.
The giants.
I'm picturing these instruments that are the size of a school bus, requiring the largest rockets we have just to get them off the ground. How can a single university team be building something that maps the entire moon? Are we talking about sending a massive new space station into lunar orbit?
That is the crucial engineering hurdle that makes this breakthrough so significant.
Yeah.
If you know anything about the history of X-ray astronomy, you know that traditional X-ray telescopes are notoriously massive.
They're huge, right?
They are some of the heaviest, most cumbersome instruments humanity has ever put into space. And there is a very specific, unforgiving physical reason for that bulk. You can't just shrink them normally.
Right. It has to do with how X-rays behave compared to normal visible light. Because I know that if I take a standard telescope mirror, like the kind you might have in your backyard to look at Jupiter, and I try to point it at an X-ray source, it just doesn't work.
It doesn't work at all. It's useless.
Why is that? Why doesn't it reflect?
Because X-rays are incredibly high-energy photons. They carry so much energy, and their wavelengths are so incredibly short that if you fire an X-ray at a standard curved optical mirror, it will not bounce off the surface and focus into an eyepiece like normal light does.
So what does it do? Does it just break the mirror?
Well, it will either be completely absorbed by the mirror's material, or it will just blast right through it, almost like the mirror wasn't even there.
Oh, wow. So I'm imagining, like, trying to bounce a tennis ball off a wall. A tennis ball bounces easily. That's our visible light. But an X-ray is like firing a high-caliber bullet at a piece of tissue paper.
That is a fantastic analogy, yes.
Mm.
The tissue paper doesn't stand a chance of deflecting that bullet. It just punches a hole straight through.
So how do you fix that? How do you catch a bullet with a mirror?
Well, because of that penetrating power, astronomers in the mid-20th century had to completely reinvent how a telescope even works in order to capture X-rays. They had to invent something called grazing incidence mirrors.
Grazing incidence. Okay, I think I know where this is going, but break down the physics for me. How do you force a high-energy bullet to actually bounce?
You have to change the angle. Think about the angle of attack. Imagine you're standing on the shore of a completely calm lake. If you take a heavy stone and throw it straight down into the water, what happens?
It just violently breaks the surface and sinks immediately.
Exactly. That is our X-ray hitting a standard mirror head-on. But if you take that exact same stone, crouch down low, and throw it at a very shallow, almost parallel angle to the water.
Oh, it skips. It skips across the surface.
Right, it skips. Even though water is soft and the stone is heavy, the extreme shallow angle forces the stone to deflect. Grazing incidence mirrors work on that exact same principle.
So instead of a dish that faces the target directly, like a satellite dish on a house, what does it look like?
X-ray mirrors are shaped like long, hollow cylinders, and they're often nested one inside the other, kind of like Russian nesting dolls.
Wait, hollow cylinders. How does the light get in?
The incoming X-rays enter the open top of the cylinder, and because the walls are angled at just a fraction of a degree, the X-rays skip off the ultra-smooth inside surface.
Like the stone on the pond.
Precisely. They skip, and they are slowly funneled down a long tube until they hit a detector at the far end.
I see the problem immediately, though. To skip an X-ray down a tube and actually bring it to a focused point, that tube has to be incredibly long.
It has to be immensely long. The focal lengths required to gently guide these high-energy photons requires so much physical space. So the telescope ends up being 10, 15, or even 20 meters long.
That's the size of a building.
It is. And they are incredibly heavy due to the layers of dense metal required to make those nested cylindrical mirrors, which means they are astronomically expensive to launch.
So if you want to put a massive X-ray observatory into orbit around the Earth, you put it on top of a heavy lift rocket, blast it into low Earth orbit, and you just leave it there. And we've done that.
We have. It takes massive resources, but we do it.
But sending something that huge all the way to the moon, I mean, that's a completely different mathematical universe, isn't it?
It is an absolute logistical nightmare. Launching a massive payload from Earth's surface is hard enough. But pushing a school bus-sized instrument across the 250,000 miles to the moon...
Yeah, that takes so much fuel.
And not just to get it there. You have to carry enough heavy rocket fuel to physically slow that massive object down once it arrives, so it doesn't just fly right past the moon and into deep space.
Oh, right, you have to hit the brakes.
Exactly. The fuel requirements alone for lunar orbit insertion of a traditional X-ray observatory would bankrupt most space agencies. It's just not feasible.
Which brings us directly to the core of the Tokyo Metropolitan University breakthrough. If traditional telescopes are heavy, long, and basically impossible to maneuver into a tight lunar orbit, what did Toyota and Izoi actually build?
They built a telescope that completely upends those traditional engineering constraints. The instrument they've designed does not weigh thousands of kilograms. The entire sensor payload weighs less than 10 kilograms.
Wait, I need to stop you there. 10 kilograms.
Less than 10 kilograms, yes.
This is roughly the weight of a medium-sized dog or like a couple of bags of groceries. How is it physically possible to replace a 20-meter-long, multi-ton orbital observatory with something I could carry onto an airplane as hand luggage?
It sounds impossible, I know.
What is the catch here? Because, you know, in physics, you can't cheat the rules. There is always a catch.
It's the exact right question to ask. You cannot cheat physics. The high-energy nature of X-rays hasn't magically changed. What is fascinating here is that the catch isn't a loss of precision or some magical new element.
So what is it?
It is a brilliant, radical change in engineering strategy. And to understand that strategy, we actually have to look at where this technology was born, because this ultra-lightweight telescope was not originally invented to look at the moon at all.
Really? What was it for?
It was initially developed to study Earth's magnetosphere.
So this entire lunar mapping project is actually a pivot from a totally different mission.
A magnificent opportunistic pivot.
Yes!
For years, researchers have been trying to figure out how to put highly sensitive, extremely lightweight X-ray detectors into orbit around Earth.
To monitor what exactly?
And monitor how the violent solar wind interacts with our planet's magnetic shield. They needed an instrument that was nimble, something that could be launched cheaply in large clusters.
Ah, okay. So they needed something small.
Right, so material scientists and astrophysicists collaborated, and they developed something called micropore optics.
Micropore optics. Okay, I'm guessing micro means we are shrinking those giant skipping stone cylinders down. But how do you shrink a 20-meter telescope mirror?
You basically replace those massive, heavy nested metal cylinders with incredibly thin, lightweight plates. Imagine a plate made of advanced silicon or glass that is absolutely riddled with microscopic holes.
Like a sponge.
Kind of, but much more structured. These aren't just random round holes drilled into a plate. They are perfectly structured microscopic square pores.
I am struggling to visualize this a bit. Why square pores? And how small are we actually talking?
We are talking about pores that are fractions of a millimeter wide, tiny. And the reason they are square is critical to the physics of focusing the X-ray.
How does the square shape help focus it?
Well, when an X-ray enters a microscopic square pore, it skips off the flat internal walls of that tiny tunnel. By having a square geometry, the X-ray can reflect off two adjacent walls in sequence.
So it hits like the top wall and then immediately hits the side wall.
Exactly. This double reflection inside the microscopic pore mimics the exact same shallow grazing incidence funneling effect of the giant metal cylinders we talked about earlier.
Oh, but it accomplishes it in a fraction of the distance.
Yes. You get the exact same skipping stone effect, but shrunk down to the microscopic level.
So instead of one giant tube slowly funneling a photon over 20 meters, you have millions of microscopic square tubes rapidly funneling millions of photons over a distance of just a few centimeters.
That is the exact mechanism. You're replacing brute force mass with hyper-engineered geometry. The X-rays skip through these microscopic pores just like they do through the giant orbital observatories, but the whole apparatus is shrunk down.
And so the weight drops from tons to kilograms.
Precisely. From a school bus to a bag of groceries.
It sounds so similar to the evolution of computing to me, like moving from those giant room-sized vacuum tube computers of the 1950s down to a modern silicon microchip.
That is a very solid parallel. You aren't changing the fundamental math of computing, or in this case, the physics of X-rays. You are just miniaturizing the physical architecture that performs the task.
That's brilliant.
And when the team at TMU, led by Toyota and Izoi, look at the performance specifications of this micropore technology, they realize something profound.
They realized it was perfect for the moon.
Exactly. They realized they were holding the perfect tool for a lunar orbital mission. But the brilliance of their proposal doesn't stop at just sending one of these small telescopes to the moon.
What do you mean? They're sending more than one?
Because the individual units are so incredibly lightweight and small, a single lunar orbiting satellite doesn't have to carry just one sensor. It can carry a grid of them.
Oh, they're packing multiples onto one satellite.
Specifically, they have designed a system that utilizes a 5x5 array. That's 25 individual micropore X-ray telescopes, all mounted together on a single lightweight orbital platform.
I love the elegance of this concept. If you have a 10-kilogram sensor, you don't just celebrate that it's light and launch one, you take advantage of that weight savings to multiply your observational power.
Absolutely. It's incredibly efficient.
It immediately reminds me of the compound eye of a fly.
Oh, how so?
Well, a human eye is essentially one massive lens trying to take in a wide field of view. But a fly doesn't have the space or mass for a giant, heavy eye. So nature gave it thousands of tiny, highly efficient individual lenses, right? Ommatidia.
Right, the little facets.
Yeah. Each one captures a tiny sliver of light, but when the fly's brain stitches all those slivers together, it gets this massive, wide-angle, highly sensitive view of its entire environment. The 5x5 array is basically a mechanical compound eye.
That analogy hits the nail right on the head.
Yeah.
By utilizing a 5x5 array of micropore telescopes, the TMU team is exponentially compounding the power of the instrument.
Because if you only had one, you'd just be looking through a straw.
Exactly. If you only had one small telescope in lunar orbit, you would be looking at a tiny pinprick of the lunar regolith at any given moment. It would take millennia to map the whole surface.
But with the array...
With the array, you are sweeping a massive wide net across the regolith as the satellite orbits. You dramatically increase the coverage area and the overall speed of data collection.
So the catch I asked about earlier really isn't a compromise in the quality of the science at all. It is just a completely different engineering philosophy.
Precisely. Instead of building one giant heavy ducket to catch X-rays slowly, we are casting a wide net of tiny, hyper-efficient buckets to catch them rapidly.
We are utilizing a smart, distributed, geometric design rather than brute force physical mass. I love that. But we have to remember, the design of the telescope array itself is only half of the equation, right?
Right. The telescope is just a passive receiver.
It is essentially just a very fancy camera lens sitting in the dark. To understand how we can actually map the chemical elements of the moon, we need to understand the source of the signal. We need a flash of light.
Yes. Because this telescope isn't shooting X-rays down at the moon like a radar dish.
It's waiting for something to happen.
It is. And that something is an incredibly violent interaction between the moon and the sun.
Let's dive into the cosmic physics here, specifically this mechanism called X-ray fluorescence, because this is the cool part.
Oh, X-ray fluorescence, or XRF, is one of the most elegant and reliable mechanisms in all of astrophysics. It is the core physical process that makes this entire mission possible.
Okay, so how does it work? How does XRF let us map a giant rock?
Well, to truly grasp how it allows us to map a celestial body, we actually need to zoom all the way down to the microscopic atomic level. Think about the lunar surface.
Okay, the dirt, the rocks.
Every rock, every boulder, every single grain of that fine abrasive dust we call regolith is made of atoms. You have oxygen, magnesium, aluminum, silicon, iron.
The fundamental building blocks of planetary geology.
Correct. And in a normal calm state, these atoms are just sitting there on the lunar surface doing nothing. To an X-ray telescope, they're completely dark. They're not emitting any high-energy radiation on their own.
So the telescope would just see pitch black.
Exactly. But our sun is not a calm, quiet neighbor. The sun is a raging, churning, violently magnetic ball of superheated plasma.
It's basically a continuous explosion.
And due to the complex twisting of its magnetic fields, it frequently unleashes intense solar flares.
These flares are massive eruptions, right? Like billions of megatons of energy just snapping and exploding outward into the solar system.
Yes, magnetic reconnection events. And during these events, the sun throws massive amounts of extremely high-energy X-rays out into the void of space, traveling outward at the speed of light.
I am really trying to picture the sheer scale of this. The sun erupts, and this wave of invisible high-energy X-rays washes over the entire inner solar system.
It's a cosmic tsunami of radiation.
But here on Earth, we don't really notice when a solar flare's X-rays hit us unless we are looking at specific atmospheric phenomena like the auroras or monitoring satellite interference. Why is that? Why don't we get cooked?
Because Earth has armor. We have a remarkably thick, dense atmosphere, and we have a powerful global magnetic field generated by our planet's spinning molten core.
Our shield.
Right. When those high-energy solar X-rays hit Earth, our atmosphere absorbs and scatters them long before they ever reach the surface. That atmospheric shield is the only reason complex life can exist down here.
But the moon doesn't have that. The moon has no atmosphere at all, just the hard vacuum of space right down to the dirt.
None. And it has no active global magnetic field. It is completely naked and exposed.
So when that wave hits...
When a solar flare erupts, those high-energy X-rays from the sun slam unimpeded directly into the raw, exposed lunar regolith.
Okay, here's where I really need you to explain the quantum mechanics of this, because it sounds like magic if we don't break it down. What actually happens when a high-energy solar X-ray, traveling at the speed of light, slams into a single atom of, say, aluminum sitting quietly on the lunar surface?
It's a violent microscopic collision.
Does the atom just absorb the heat? Does it shatter? What happens?
It triggers a very specific atomic reaction. Think of the aluminum atom as a miniature solar system. You have a dense nucleus in the center, and you have electrons orbiting around it in different shells or energy levels.
Like planets around a sun.
Exactly. Now, the incoming solar X-ray essentially acts like an unimaginably fast microscopic cue ball on a billiard table. It smashes into the aluminum atom with so much energy that it completely bypasses the outer electrons and strikes one of the atom's innermost electrons.
Wait, it goes straight for the inner shell.
It does. It transfers its energy and knocks that inner electron completely out of its orbit and ejects it from the atom entirely.
Wow. So the atom has just been violently assaulted by this X-ray. It has a gaping hole in its innermost shell now. I imagine the atom doesn't like being in that state.
It absolutely does not.
Okay.
In quantum mechanics, systems always seek their lowest, most stable energy state. An atom with a missing inner electron is highly unstable. It is in what we call an excited state.
It wants to fix itself.
Exactly.
Yeah.
So almost instantaneously, an electron from a higher outer orbit falls down to fill that newly created hole in the inner shell.
It drops down to restore the balance. That makes sense.
But here is the critical rule of physics. An outer electron possesses more potential energy than an inner electron. In order to drop down to that lower inner orbit, the outer electron has to shed its excess energy.
It can't just take that extra energy down with it to the inner ring.
No, it cannot. It has to release it. And it releases that exact, specific amount of energy in the form of a brand new photon, specifically an X-ray photon. The atom fluoresces.
Hence X-ray fluorescence. The atom absorbs the sun's chaotic, violent, high-energy X-ray, uses it to eject an electron, and then as it heals itself, it spits out its own brand new X-ray in response.
And this right here is the magic key that makes the entire TMU mission possible. Because the energy of the X-ray that gets spit out by the atom is not random. It is mathematically precise.
Because the distance between the electron shells is fixed.
Yes. It is completely unique to the specific element that created it. The energy difference between the outer shell and the inner shell of an aluminum atom is a very specific constant number.
So it only ever releases that exact amount of energy.
Correct. Therefore, the X-ray emitted by an aluminum atom has a totally different energy level than an X-ray emitted by a silicon atom, which is different from the energy emitted by oxygen, which is different from magnesium.
So they act like absolute, unmistakable atomic fingerprints.
They are definitive elemental signatures. An X-ray detector measures the energy of these incoming photons in units called electron volts. When the detector sees a spike at a specific number of electron volts, it knows with absolute certainty that is aluminum.
There is no guesswork.
None. When it sees a spike at a different specific energy level, it knows that is silicon.
This completely reframes the visual for me. Going back to our magic glasses idea from the beginning, it's like the sun is acting as a giant, unpredictable cosmic blacklight.
I love the blacklight comparison.
Right. The moon is just sitting there in the dark gray and monochrome. But the moment a solar flare hits, the entire surface suddenly glows in X-ray wavelength.
It lights up completely.
And if you are orbiting overhead, looking down through this 10-kilogram micropore array, you aren't just seeing a flash of white light. You are seeing different colors of this invisible spectrum.
You see the specific energy signatures.
Yeah, you see patches of the surface glowing with the exact energetic fingerprint of aluminum right next to pools glowing with the fingerprint of silicon.
That is precisely what the instrument is designed to see. The telescope sits up there in its stable lunar orbit, passively waiting. When a flare hits, it catches these characteristic X-rays as they bounce back up from the surface, sorts them by their specific energy levels, and plots them onto a geographical map of the ground directly below.
Here's where it gets really interesting to me. We are literally using solar flares, these massive, violent, sometimes terrifying eruptions on our star as a giant flashlight to read the chemical dirt on the moon.
We are.
We are hijacking the sun's fury to do our scientific surveying for us, basically for free. But wait, this brings up a very obvious logistical hurdle that we definitely need to address.
I suspect I know exactly what you're going to ask.
Solar flares are notoriously unpredictable. I mean, we cannot schedule them.
No, we certainly can't.
We have a general understanding of the 11-year solar cycle, solar maximum and solar minimum, but we cannot predict a specific flare with pinpoint accuracy.
It's space weather. It's chaotic.
Sometimes the sun is incredibly active, throwing out flares every day, and sometimes it is stubbornly quiet for weeks or even months at a time. If our telescope only works when the sun flares, doesn't that make mapping the entire moon a massive, frustrating waiting game?
It absolutely makes it a waiting game. There's no getting around that. You cannot just send this satellite up for a long weekend, snap a global picture, and come home.
Because it might not flash while you're there.
Exactly. You are entirely at the mercy of the space weather environment. If the sun is quiet, your highly advanced X-ray telescope is essentially blind. It is seeing almost nothing but cosmic background noise.
So how long does it actually take to build a complete high-resolution map of an entire planetary body if you are just waiting for random, unpredictable flashes of light from a star 93 million miles away?
Well, this is exactly why the TMU team's specific approach with the 5x5 array is so critical. Remember when we talked about the wide net?
Oh, right. The fly's eye?
Yes. If you only had one small micropore sensor, and you only caught a tiny narrow sliver of the moon's surface during a brief flare, it would take centuries of orbiting to piece together a full map.
Because the odds of you looking at the right spot at the exact right millisecond are so low.
The probability would be incredibly low. But because you have a wide field of view provided by the distributed array, every single time the sun flares, you cast a massive net. You illuminate and capture a huge swath of the surface simultaneously.
You're capturing a much bigger chunk of the jigsaw puzzle with every single flash.
Exactly. The complex orbital simulations run by Toyota and Professor Izoi suggest that by maintaining this orbital vigilance, just passively flying over the surface and catching these flashes whenever the sun decides to cooperate, you could achieve a full, comprehensive map of the moon's surface chemistry in just a few years of continuous observation.
Just a few years. That's actually amazing. It is like building a massive long exposure photograph. You piece it together flare by flare, photon by photon, pixel by pixel, until the entire global map comes into sharp focus.
That's a great way to put it. A long exposure cosmic photograph.
Okay, so we have established the brilliant engineering. We have this lightweight micropore telescope array. We understand the cosmic physics of how we use the sun as a blacklight to trigger these atomic fingerprints via X-ray fluorescence.
The mechanism is perfectly sound.
The engineering is revolutionary.
Yeah.
But now we really have to talk about the why.
Like the scientific application of all this data.
Because once we spend those few years in orbit and we finally catch all these fluorescent fingerprints and we build this beautiful, colorful map of oxygen, magnesium, aluminum, and silicon, what story do those colors actually tell us?
They tell us the story of the moon's birth.
We need to move from the how it works to the what it means.
Yeah.
Because reading these elements across the global surface is basically like reading the deep geological bones of the moon.
It is the ultimate exercise in planetary forensics.
Fair.
And to truly understand why this new global map is so vital to planetary scientists, we have to look honestly at the data we are currently working with.
What do you mean? Don't we already know a lot about the moon?
We do. Humanity has actually known a fair bit about the moon's fundamental chemistry for decades. But our knowledge is incredibly localized. It is severely limited by geography.
Oh, you were talking about the physical samples we brought back, the Apollo missions.
Yes, the Apollo missions were a monumental, unparalleled achievement in human history. The hundreds of pounds of physical rock and regolith that those astronauts brought back to Earth completely revolutionized our understanding of the solar system.
But they only went to a few places.
Right. We have to remember the strict operational constraints of Apollo. The astronauts landed in very specific, carefully chosen, relatively flat and safe equatorial regions on the near side of the moon. Think of the Sea of Tranquility.
They couldn't exactly land in the middle of a jagged crater field.
No, it was too dangerous. And they only had a few hours or days to scoop up material from their immediate local surroundings before they had to leave.
So our current hands-on understanding of the moon's global chemical makeup is essentially based on a few tiny pinpricks of data clustered near the equator on one side of the sphere.
That is the reality. We have extrapolated a lot from those samples. But extrapolating is not the same as observing globally.
I'm trying to think of a good way to conceptualize how limited that is. It feels like trying to understand the entire complex, diverse geography of the Earth, trying to comprehend the existence of the Himalayas, the Sahara Desert, the Amazon rainforest, the deep Marianas Trench, the polar ice caps.
Where are you going with this?
By only looking at a handful of dirt you scooped up from a single backyard in a suburb of Ohio.
Oh, that is a wonderfully apt comparison. Yes. If you only looked at the dirt from that Ohio backyard, you might reasonably conclude that the entire Earth is covered in temperate, loamy soil and green grass.
You would completely miss the frozen tundra of Antarctica. You'd miss the volcanic islands of Hawaii.
You would miss the deep ocean trenches. And with the moon, we know from orbital imaging that there are massive physical and geographical differences between different regions.
Just visually, it looks totally different depending on where you look.
Exactly. We know the near side is covered in those huge, dark, flat basaltic plains we call Maria, but we know the far side looks completely different. It is heavily cratered, ancient, rugged highlands with almost no dark Maria.
The two sides of the moon barely even look like they belong to the same planet.
It's true. Furthermore, we know that the South Pole Aitken Basin on the far side is one of the largest, deepest impact craters in the entire solar system.
How deep is it?
It is so incredibly deep that it potentially excavated material from the deep lunar mantle itself. But because we only have rocks from a few backyards on the near side, we do not have a high-resolution global chemical map to connect all these massive geographical pieces together. We have theories, but we lack global chemical conformation.
So we have the corner pieces of a 1,000-piece jigsaw puzzle, but we are missing the vast majority of the picture in the middle.
And a comprehensive geochemical map finally gives us the complete picture. If we can see the precise global distribution of elements like magnesium, iron, and aluminum, we can actually reverse engineer billions of years of planetary evolution.
We can test if our theories are actually right.
Yes. It allows us to empirically test our fundamental models of how the moon formed and how it evolved in its earliest days.
Let's dig deep into that early history. When we talk about the formation of the moon, we are talking about a cataclysmic event, right? The giant impact hypothesis, followed by the magma ocean.
That is the leading scientific consensus, yes. The theory dictates that over 4 billion years ago, the very early proto-Earth was struck by another developing planet, roughly the size of Mars, which scientists call Theia.
Just a full-on planetary collision.
A glancing blow, but yes.
Yeah.
The sheer kinetic energy of that collision vaporized a massive amount of material from both bodies, blowing a ring of superheated debris into orbit around the Earth. Over time, gravity pulled that ring of debris together to form the moon.
It is a terrifying and awesome thing to visualize. Just a massive glowing sphere of liquid fire coalescing in space. The entire moon, in its infancy, was just a global ocean of molten rock.
A global magma ocean, potentially hundreds of kilometers deep. Now, as that magma ocean slowly radiated its heat away into the cold of space over millions of years, a profound geological process called differentiation occurred.
Let's break down the mechanics of differentiation, because I am trying to picture this. Without wind or weather or tectonic plates like we have on modern Earth, wouldn't a ball of liquid rock just cool down into one solid, uniform, evenly mixed sphere of gray rock? Why does it change?
Because of gravity and the varying densities of different minerals. Even though it was a liquid ocean, it was a liquid suspended in a gravitational field. As the magma slowly cooled, different minerals began to crystallize at different temperatures.
Meaning they turn from liquid to solid at different times.
Right. This is a process called fractional crystallization.
Okay, so the liquid rock starts turning into solid crystals, but not all at once.
Exactly. And as these crystals form, they respond to gravity. The heavier, denser minerals, specifically those rich in iron and magnesium, like olivine and pyroxene, crystallized and physically sank down toward the center of the moon.
Like heavy sand sinking in a pool of water.
Yes. Over millions of years, this sinking material formed the deep, dense lunar mantle.
The heady stuff sinks to the bottom of the ocean. What about the rest?
Well, meanwhile, lighter minerals were also crystallizing. Specifically, a mineral called plagioclase feldspar, which is heavily rich in aluminum and calcium.
And because it's lighter.
Because this mineral was significantly lighter and less dense than the surrounding magma, it did not sink. It floated to the top of the magma ocean.
Oh, like foam on top of a cappuccino?
That's exactly it. It essentially formed a massive global scum of lightweight rock floating on the surface. As the ocean finally cooled completely, that floating layer of aluminum-rich rock solidified to become the primary crust of the moon.
The ancient lunar highlands. So according to this model, the original outer shell of the moon should be absolutely packed with that lightweight aluminum, while all the heavy magnesium and iron should be locked away deep underground.
Yes. And this is exactly why the X-ray fluorescence map from our tiny telescope is so crucial. If we can map the exact concentrations of aluminum versus magnesium globally, we can mathematically prove, refine, or even challenge the parameters of this magma ocean model.
We can see if it actually happened that way everywhere.
We can see exactly how thick the aluminum crust is in different regions. We can see if the differentiation process was uniform or if it was interrupted or altered in certain areas.
But the moon isn't just a perfectly pristine, layered jawbreaker today, right? That crust didn't just sit there untouched for 4 billion years. It has been abused.
It has suffered relentless abuse. And that brings us to the second major geological gap this X-ray map will fill: the violent volcanic and impact history of the moon.
Because over the last 4 billion years, the moon has been relentlessly bombarded by asteroids and comets.
The late heavy bombardment in just billions of years of random space rock smashing into it.
And some of those impacts were huge.
Beyond huge. Some of these asteroid impacts were so unimaginably colossal that they didn't just dent the surface. They punched completely through the outer light aluminum crust, and they physically excavated the heavy, dense magnesium and iron-rich mantle from deep below.
They essentially acted as cosmic drills, digging up the buried layers and splashing them all over the surface.
Right. And furthermore, later in the moon's history, massive internal volcanic eruptions brought molten basalt from deep inside the moon up to the surface.
Is that where the dark spots come from?
Yes. This heavy lava flowed out, filling in the giant impact basins and creating those dark patches, the Maria, that we see from Earth today.
So when our tiny TMU X-ray telescope is orbiting the moon, sweeping over a region of ancient highlands, and it suddenly sees a massive, unexpected spike in the elemental signature of magnesium right in the middle of an area that should be pure aluminum crust, scientists know exactly what they're looking at.
They absolutely do. They're looking at a location where a giant asteroid penetrated the crust and brought the deep interior up to the surface for us to analyze.
If we connect this to the bigger picture, the entire surface of the moon is just a written chemical record of the violent history of the early solar system.
It is a diary of catastrophe.
Every single asteroid impact, every single ancient lava flow left a permanent chemical signature. By mapping the exact distribution of these elements globally, we aren't just looking at interesting, colorful rocks. We are reading the history book of our cosmic neighborhood.
We are learning the fundamental mechanics of how planets coalesce from dust, how they differentiate into layers, how they evolve over eons, and how they endure cosmic bombardment.
It is incredibly profound to think about. We are using microscopic atomic fingerprints triggered by violent solar flares to read a geological history book that was written billions of years before the first single-celled life even existed on Earth.
It is pure, awe-inspiring science.
But as thrilling as all that deep ancient history is, there's an entirely different side to this coin. Understanding the moon's past is intellectually fascinating, but this chemical map has a highly practical, incredibly urgent application for humanity's immediate future.
Oh, absolutely. This isn't just academic.
We aren't just matching the past, we are drawing the literal roadmap to the future.
And this is where the theoretical astrophysics meets hard, logistical reality. Because as everyone paying attention to space exploration knows, humanity is not content to just look at the moon through telescopes anymore. We are actively preparing to go back.
We are going back, and this time we are planning to stay. We are talking about the Artemis program and the massive international effort to establish a sustained, permanent, human presence on the lunar surface.
It is a completely different mission profile than Apollo.
Right. We are not talking about planting a flag, leaving some footprints, and coming home a few days later like the Apollo era. We are talking about building base camps. We are talking about pressurized habitats, lunar rovers, power stations, a permanent foothold on another world.
And establishing a permanent foothold requires a completely different operational mindset than a brief exploratory visit. Consider the logistics of exploration on Earth.
Okay, like going camping.
Exactly. If you go camping for the weekend, you can easily pack all your drinking water, all your food, and your nylon tent in the trunk of your car. You bring everything with you, and you bring your trash home.
Easy enough.
But if you are moving into the deep wilderness permanently to build a cabin and live there year-round, you cannot possibly bring a lifetime supply of water and lumber in your car. It's impossible.
You have to learn how to live off the land. You have to chop local wood, find a local stream, hunt local food.
And living off the land in the unforgiving vacuum of space is governed by a critical engineering concept. It's a very clunky acronym, but it might be the most important term in all of space exploration. ISRU.
ISRU. In situ resource utilization.
Yes. It simply means utilizing the physical resources you find naturally occurring at your destination rather than bringing them all the way from Earth.
And ISRU is not just a neat idea. It is a mandatory requirement for human survival in space, right?
It is absolutely non-negotiable.
Let's explore why it's mandatory, because it all comes down to the brutal physics of gravity wells and the rocket equation. Bringing things from the surface of the Earth to the surface of the moon is mind-bogglingly expensive.
It takes massive amounts of fuel just to lift a tiny amount of mass out of Earth's gravity. It currently costs thousands and thousands of dollars to launch a single kilogram of mass into orbit.
A single kilogram. So if we want to build a sprawling lunar habitat, we simply cannot afford to launch every single steel beam, every single heavy solar panel, and every single drop of drinking water on top of a giant rocket.
We would bankrupt the global economy before we even poured the concrete for the foundation.
The gravity well of Earth is basically a tyrannical accountant. It punishes every ounce of mass you try to take with you.
That's a brutal way to put it, but it's completely accurate. To survive long-term on the moon and to eventually push onward to build colonies on Mars, we have to find what we need on the moon.
We have to become cosmic scavengers and miners.
We do. And this is exactly where our 10-kilogram micropore X-ray telescope suddenly transitions from a purely scientific instrument into the most valuable prospecting tool in the solar system.
Because it isn't just looking for common rocks to validate ancient geological theories, it is actively, globally, hunting for the vital resources hidden in the dusty regolith.
It's looking for the gold mines.
So what specific resources are we talking about here? When a mission planner at NASA looks at this glowing X-ray map, what are the gold mines they are desperately searching for?
There are two main categories of resources that are absolutely critical for ISRU. First, we are looking for the widespread distribution of specific industrial metals and rare earth elements. We're looking for high concentrations of titanium, iron, and aluminum.
Structural metals, things we can build with.
Exactly. If we're going to build robust structures on the moon habitats, landing pads, blast shields, we need to know where the highest concentrations of structural metals are located.
And what about power?
If we want to build sprawling fields of solar panels to generate power during a lunar day, we need to locate massive deposits of silicon. The technology exists to literally scoop up the lunar regolith, refine it using solar furnaces, extract the metals, and 3D print our habitats directly from the lunar dirt.
That is wild, 3D printing a house from moon dirt.
But that entire industrial process only works if we know exactly where the richest, most accessible veins of ore are located. You don't build a massive mining facility in an area with low-grade dirt.
Okay, so building materials and power generation. That makes perfect logistical sense. But there is something even more fundamental than building materials. You can survive without a steel beam for a few days, but there is one resource you cannot survive without.
The most universally valuable substance in the cosmos for human beings. Water.
Water. Every deep space mission, every search for life, every colonization plan, it always comes back to water.
Because it is the foundation of human biology and, surprisingly, the foundation of our spacefaring infrastructure.
Now, the X-ray telescope itself is primarily looking for elemental fingerprints like oxygen, right? Not water molecules directly.
Correct. And while oxygen is locked up in silicate rocks everywhere on the moon, scientists are specifically hoping to correlate these highly detailed elemental maps of oxygen and other trace elements with existing data from other orbiters.
To find the water.
Yes, to locate high concentrations of water-related compounds. Finding the precise location and volume of water is the key to unlocking the entire solar system.
Let's really break down why water is so critical, because I think a lot of people just assume it's only for astronauts to drink. Obviously, biological hydration is paramount, but water in a space colony is basically a miraculous Swiss Army knife.
It truly is. Yes, you need it for direct life support, drinking, sanitation, and growing food in hydroponic or aeroponic agricultural bays. But water has incredible physical properties that make it essential for survival.
Physical properties, like what?
It is incredibly dense, and its molecular structure makes it one of the absolute best available shields against dangerous cosmic radiation.
Wait, let me stop you there. Water acts as armor. How does water stop radiation better than, say, a thick sheet of lead?
It has to do with the specific type of radiation astronauts face in deep space. They are bombarded by galactic cosmic rays and solar particle events, which are essentially high-energy protons screaming through space at near the speed of light.
Okay, so these protons are just flying everywhere.
Yes. If a high-energy proton hits a heavy element like lead, it can actually shatter the lead nucleus, creating a shower of secondary radiation that is incredibly dangerous to human tissue.
It makes it worse.
In a way, yes. But water is H2O, 2 parts hydrogen. A hydrogen nucleus is basically just a single proton. So when a high-energy cosmic proton hits the hydrogen in water, it's like 2 billiard balls of the exact same mass colliding.
The incoming proton just stops.
The incoming proton transfers its energy efficiently, slowing down rapidly without creating a dangerous shower of secondary radiation.
That is fascinating. So if you want to build a safe lunar habitat, you don't necessarily need to drag massive lead plates from Earth. You just build double-walled habitats and pump your water supply into the walls.
You literally live inside a giant protective water balloon.
That is brilliant. So it is hydration, it is agriculture, and it is vital armor. But there is one more massive, game-changing application for water on the moon, and it relies on the basic chemistry of the molecule itself. H2O. 2 parts hydrogen, 1 part oxygen.
I know exactly where this is going.
If you have a sprawling field of solar panels providing abundant electricity during the 2-week lunar day, you can pass a strong electric current directly through that water.
A simple, well-understood process called electrolysis. When you pass electricity through water, you break the chemical bonds. You split the water molecule apart into its constituent gases, hydrogen gas and oxygen gas.
And what do you get when you capture liquid hydrogen and liquid oxygen? pipe them into a combustion chamber, and ignite them.
You get rocket fuel, specifically hydrolox. It is the most powerful, most efficient chemical propellant humanity currently possesses. It is the exact same fuel that powered the space shuttle main engines and the core stage of the massive Artemis SLS rocket.
This is the absolute game changer for human expansion. If we find abundant, accessible water on the moon, and we use solar power to refine it into fuel, the moon stops being just a remote scientific outpost.
It becomes a cosmic gas station.
Exactly. It becomes the critical port from which we launch massive missions to Mars, the asteroid belt, and the outer solar system.
Because the economics of space travel completely change at that point. Launching a fully fueled massive rocket from the deep gravity well of Earth requires an agonizing amount of energy.
It's so hard to get off this planet.
It really is. But launching that same rocket from the moon, which has only 1/6 of Earth's gravity and no atmospheric drag to fight against, it takes a tiny fraction of the fuel. You can launch massive payloads across the solar system if you just fuel up at the moon first.
But we can only turn the moon into a gas station, a shipyard, and a permanent thriving colony if we know exactly where the resources are physically located.
Exactly. And that brings us to the ultimate impact of the TMU mission.
So, what does this all mean for the immediate future of the Artemis program? If we send this 10-kilogram micropore array up into orbit, and it spends a few years meticulously mapping the surface, reading the atomic fingerprints triggered by solar flares.
And it builds that complete map.
Right. And what if it finds incredibly high concentrations of water-related compounds or easily accessible shallow veins of structural titanium in a specific unexpected region? Does this fundamentally change where humanity decides to build its first permanent base?
I would argue it changes everything. Yeah. Right now, almost all the focus for Artemis is targeted at the lunar South Pole.
Why the South Pole?
Because radar and neutron spectrometers have hinted at the presence of water ice hidden deep inside permanently shadowed craters there.
But I've read about those craters. They are nightmarish environments to operate in. They are freezing, plunged in eternal darkness, and the terrain is incredibly rugged and dangerous for landers and rovers.
They are arguably the most hostile environment we could possibly choose to build our first colony. We are targeting them out of desperation, basically, because we think that's where the only water is.
What if the map changes that?
What if the high-resolution global chemical map generated by Toyota and ESO's telescope reveals a completely different reality? What if it finds a massive, easily extractable concentration of vital elements right near the equator in a flat, safe area bathed in constant, predictable sunlight for endless solar power?
The map dictates the real estate.
The map is everything. This data is essentially the ultimate real estate guide for future lunar colonies. You do not build a massive, complex mining town in a perilous ravine if there's no gold there. You build it where the resources are richest, safest, and most accessible.
It makes perfect sense.
The data provided by this specific, revolutionary technological breakthrough from Tokyo Metropolitan University will be the foundational text that mission planners at NASA, ESA, JXAs, and commercial spaceflight companies use to literally draw the physical borders of humanity's first off-world settlements.
It is stunning to take a step back and think about the chain of events here. We are talking about a piece of technology that weighs less than a bag of groceries. A piece of technology that was originally designed for a completely different purpose, to look at Earth's magnetic field and solar wind interaction.
This incredible pivot.
But through brilliant observation and adaptation, it pivots to lunar orbit, uses the violent eruptions of the sun as a tool, maps the atomic history of a dead world, and ultimately becomes the compass that guides humanity's permanent settlement of the solar system.
It is the perfect, beautiful example of how the scientific pursuit operates. Discovery is rarely a straight line.
It really isn't.
You solve a complex engineering problem in one specific field, like how to make a lightweight X-ray sensor for the magnetosphere, and it unexpectedly unlocks the door to a completely different, monumental achievement in planetary geology and human survival.
Tools like this compact X-ray telescope are the absolutely necessary precursors to humanity transitioning from a single planet species into a true multiplanetary civilization.
They absolutely are.
Okay, let's take a breath and recap the incredible multi-billion-year journey we've just been on today. We started with a 10-kilogram bundle of microscopic square pores, a brilliant pivot by the team at Tokyo Metropolitan University that solved the crushing weight problem of traditional X-ray astronomy.
We explored the deep quantum mechanics of how this tiny array utilizes the violent, unpredictable solar flares of our sun as a cosmic flashlight,
Triggering microscopic atomic reactions to reveal the invisible fingerprints of the lunar dust.
We saw how those specific fingerprints, oxygen, magnesium, aluminum, silicon, allow us to peel back billions of years of silent history.
Revealing the chaotic story of a molten magma ocean, planetary differentiation driven by gravity, and cataclysmic asteroid impacts that relentlessly churned the lunar crust.
And finally, we connected that ancient, violent history to our immediate, ambitious future.
Seeing how mapping those exact same elements will guide the Artemis missions, locate the vital resources needed for in situ resource utilization, and literally draw the map for where humanity will build its permanent homes on the moon. It is a profound convergence of cutting-edge engineering, deep astrophysics, ancient geology, and bold human ambition.
It represents a turning point in our relationship with the cosmos.
It really does.
Yeah.
And before we wrap up today, I want to leave you with one final mind-expanding idea to ponder. We've spent this entire time talking about the moon, our closest neighbor, but think about the scale and the modularity of this new technology.
Oh, this is the really exciting part.
If a single 10-kilogram telescope array can map the entire chemical composition of an entire moon using just the ambient background radiation of our sun, what happens next?
The implications for the rest of the solar system are staggering.
Imagine what happens when we start mass-producing these tiny, highly efficient micropore sensors. We do not have to stop at the moon. What happens when we send swarms of these arrays out to map the thousands of unprobed asteroids in the main asteroid belt, looking for incredibly valuable deposits of platinum, palladium, and rare earth metals?
We're sending them further out.
Exactly. What happens when we send them into orbit around Phobos and Deimos, the tiny, mysterious moons of Mars, to see if they hold the specific resources we need to fuel and build a sprawling Martian colony?
Because they are so incredibly lightweight and draw so little power, they do not require massive, multi-billion-dollar flagship missions of their own. They can simply hitch a ride as secondary payloads on almost any interplanetary probe we launch in the future.
They just become standard equipment.
Exactly.
We aren't just looking at a new way to understand our moon. We are looking at the exact blueprint for how humanity will eventually prospect, map, and utilize the entire solar system. The technology developed by Toyota and ESO is the key that unlocks the door to an age of true, sustainable cosmic exploration.
It changes our relationship with space from one of brief, tentative observation to one of deep, sustainable interaction. We move from being temporary visitors to becoming permanent residents.
And it all starts with looking at things just a little differently, taking the tools we have and applying them in bold new ways. Thank you so much for joining us on this exploration today. The next time you step outside on a clear night and look up at that seemingly dead, dusty gray sphere in the sky, I want you to remember what is really up there. Think about the hidden elements. Think about the atomic fingerprints waiting to be illuminated by the fire of the sun. And keep wondering what vibrant hidden colors are glowing right beneath the dust, waiting for us to finally put on the magic glasses and see them.